design of sequential circuits. Now, what are sequential circuits? Sequential circuits are digital circuits which has the capability of storing data. Okay, so if there is a digital circuit which involves storage elements, then we call them sequential circuit. And often sequential circuit contain combinational circuit as a part of it, but combination circuit alone does not make sequential circuit. You should have storage element along with the combination circuit. With or without combination circuit, if you have storage element, then it is called sequential circuit. You can have sequential circuit just with storage elements like flip-flops without any combination circuit, but you could have in addition to it presence of combination circuit. So if you do a block diagram, then so as I said, combination circuit can be part of it. So this is a block which contains combinational part, to which you are giving inputs, external inputs, and there could be many inputs. So these are external inputs, and then from the output there are two kinds of outputs. One that goes to storage element, okay, and then the output of the storage element is also fed back as input. Okay, so there could be multiple output here also. They are fed back as storage elements. So this is basically the state Q, QA, QB, QC, etc. Depending upon how many bit we are storing, you will have that many number of outputs available, and then that is fed back into the combinational circuit, and then some of the combinational circuit output goes into the input of storage elements, and some other output we treat them as external. So these are multiple output which are available to the external. So these are external output. Okay, so this is one way you can draw the block diagram of a sequential circuit. It contains, the most important thing is the storage element. That is what qualifies it to be a sequential circuit. But along with that, you can have a combinational circuit part also, and the combinational circuit will take inputs from outside as well as from the output of the storage element. Okay, so storage element could be designed using any of the popular flip-flops. Okay, it could be registers also, which is like a group of flip-flops. So the typical flip-flops that we use are D flip-flop, so it could be D flip-flop, T flip-flop, JK flip-flop. Okay, it could be registers, etc. Okay, so which is basically group of flip-flops. So that's basically the storage element, and then the storage element will be driven by a clock. It could be either active low or active high. Okay, so what I have drawn is basically a active high input. So this is the clock input. So that is an additional thing. Of course, the you can store even without clock, but then there is no control concerning the activity that so it may result in some instability due to the free running. So the delay is the only factor that would control, but that is not very reliable. So always we would like every operation in a sequential circuit to be synchronized with a clock, and therefore we use an external clock which will go into all the storage element parts. Every flip-flop or every register inside will change its state only during the active edge of the clock. So that way we can achieve a control. Okay, so so this is a block diagram which I have shown you, and if you look at the external output, what you can see is that it is a function of the present input. As you can see, the external input is coming. So whatever is coming at the external output, it would basically depend upon two factors. One is like this external inputs, and the other is basically the state of the flip-flop. Okay, so the state of the flip-flops is basically depending upon the previous input. Okay, so previous inputs or functions of previous inputs are basically stored in the storage element, and the external output depends upon the present external inputs and the previous external inputs through the storage element. Okay, so that's the definition of a sequential circuit. Any circuit which depends upon the present and past inputs. Okay, in combinational circuit, the current output depends only on the current input. It doesn't depend upon the previous input. But in sequential circuit, it not only depends upon the present input, it can depend upon the previous inputs through the storage element. Okay, now sequential circuit can be classified into two categories. One is called Mealy, and the other is called Murray. Okay, Mealy and Murray. So what I have drawn here, if you look at, this is basically the case of Mealy. So it's called Mealy machine. Okay, you can call it as Mealy machine, the way I have drawn it. But the alternate way you can draw is again these blocks will be there, combinational block will be there. So this is the combinational circuit, and the external input is coming, and these are given into the storage element, and then the output is basically taken from the storage element. Okay, so so there is a number of lines which I am feeding back. So these are the external input, and the state directly or through some additional combinational circuit. Combinational circuit 2. Okay, so that gives you the external output. So this is another scenario. There is only a slight difference. I will tell you what is the difference. Again, this is also combinational circuit, but this is the what is called as the Murray machine. Now, what is the major difference? The major difference is that the external output depends only on the output of the storage element. Okay, it doesn't depend upon the present input. Okay, so earlier if you compare, you can see that it depends on the external output depends upon the present input as well as the previous output, but here the external output actually depends upon only the previous output. Okay, because the external outputs are taken from the storage element. So therefore whatever stored in the flip-flops are basically depending upon the earlier inputs. It doesn't depend upon the present input, because only in the next clock cycle that will be coming into the storage element. By that time the external input will also change when it goes to the next clock cycle. So it will never the storage element can never hold data that is depending upon the that depends upon the present input. It always stored data is always stored which is actually depending upon the previous inputs. So if the external output depends only on the previous input and not on the current input, then we call such sequential circuit as Murray machine. Okay, I hope the difference is clear. And so what is the or what is implication? The implication is that you need basically, so there is also a clock here also. So you need an extra clock here, okay, to reach that output, because you need to wait for the input to come up to some level where it will begin to show the output. So one more clock cycle is required to take the last part of the input. Okay, so you need more number of states also in order to create the required external output. So if I compare the Mealy machine and the Moore machine, so Mealy machine and Moore machine, both are sequential circuit. So so major difference is that output depends on present and past inputs. Okay, number one. Here output depends only on past inputs. Okay, and number two, require minimum number of clock cycle. Here one additional clock cycle. And then the next difference, what about the number of states? Requires lesser number of states. Here again requires additional, so it requires additional states, and because of that actually one additional clock. for generating the same output, for generating the same output. Okay, so whatever output is generated by the Mealy machine, to generate the same output, we require one additional clock, one additional state. So these are two ways in which you can design. Okay, so now let's take an example, the popular example which always people do is sequential one bit input is there, which is continually coming into the system, and then we will look for a particular pattern. So let's take that example, the example of a sequence detector. Sequence detector. Okay, so we have to first of all fix what is the sequence. If a stream of data is coming, like a 1 bit data is coming into the system, and it is keep on changing, like 0 1 1 1 0, like that it is keep on changing. A stream of bits is coming, and we need to look for a particular pattern, continuously look for a particular pattern, and whenever a particular pattern is detected, immediately we need to give an output high. Okay, so let's first of all decide what is the length of the pattern that we are looking. Suppose let's take the example of to detect a 4-bit sequence. So 4-bit sequence, let's say 1 0 1 0. This is the sequence that I am looking for. So there is a external input. I am going to call now that input as X, and then I am going to write the stream of bits which are coming at the input X. So let's say 0, initially it is at 0, and then 1 1 0 0 0 1 0 0 0 1 1 0 1 0 1 0 1 1 1 0. So some random sequence. Okay, so and it goes on, and I would like to state that this is the increasing time. So this is the first bit that came, and then the next bit. This is how we are now writing it, and we should interpret it as the increasing toward right increasing time. And then suppose we have an output, let's call it as Y. So it has to look for this sequence. So if you see that where is the first time 1 0 1 0 comes, and you can see that here there is a 1 0 1 0, and then you can think about considering this as another 1 0 1 0. So then this is called overlapping sequence. So whenever this is detected, whenever the final input comes, that is the time I want the output to become 1. Okay, so whenever the 4th bit is also detected, I should make it as 1. So before that there is no other place I am having 1 0 1 0. So let me just put one more here, so that I will have one more detection here, and then 0. Okay, so this is a sequence that we are considering, and if I write the output, so as long as there is no detection of sequence, or only a partial detection of the sequence that we are looking, we will have output 0. Okay, so far we have not detected, but when the next bit comes, then I would like to have a 1 there. And then if I consider the last 2 bits as that could be part of the next sequence. So if I want a design in that manner, then I'll have 0 here, because the last 4 bit now is like 0 1 0 1. That's not what I wanted. But if I go one more bit, then I will have a 1 there. Okay, so these are like overlapped sequence. Okay, but if I don't want to overlap, this particular bit will not be 1, it will be 0. Okay, so we have 3 detection. So this is the output corresponding to overlapped detection. Okay, so if I don't want the overlapping, and then this particular bit will not be 1, it will be 0, because that's not a new sequence, it's actually overlapped with the previous sequence. So I have an option to design whether I need a overlapped detection or a non-overlapping detection. So accordingly, my specification will be different and my design will differ. Now, what is the first step in designing a sequential circuit? So first step is like to draw the state diagram. So step 1. Okay, so design, we are going to design now. So the step 1 is draw the state diagram. Now, depending upon what kind of machine that you are going to design, you have an option either to draw the state diagram for Mealy machine, or you can also draw for Moore machine. So first of all, let us do it for Mealy machine. So I'm going to put Mealy. Okay. So what are my states here? So that all these designs will have finite number of states, and therefore we have a different name called FSM. So FSM stands for finite state machine. That's another name for synchronous circuit, which is either Mealy or Moore machine. They both have a finite number of states. So this is a very common jargon, finite state machine. Okay, so let's put in the finite states that we would require for designing a Mealy machine for detecting this 1010 sequence. So first thing is that we have not yet started detecting any sequence. For example, the initial bit is 0. So we have not even made any progress in detecting the 4-bit sequence. So if at all we need to detect the 4-bit sequence 1010, the first bit that should come or we should get is 1, followed by a 0, followed by a 1, and then followed by another 0. But suppose it is only a stream of 0 that is coming, we have not made any progress. So in order to distinguish the fact that we have not yet started receiving any of the bit, so we have a state assigned for that. Let's call that state as S0. So we will call the state S0. This is the state. So these are states, and state S0 means not yet detected, not yet detected a single bit. So we have not even started detecting anything, so even a single bit is not detected, so that state is called S0. And then we move on. When we get a progress from S0, we can move on to another state, S1, where we say that for example, this is a case like when the first one came, we have made we got some kind of hope that maybe our required sequence is going to start, but we don't know what is going to be the next bit, but at least we made one step progress. Okay, so this denote detection of the first bit. In our case, it is 1. When you detect 1, the first one that comes, so that is the first bit that we are looking for. And then after detecting the first bit, we are looking for whether after this 0 will come or not. So we got the first one, so we are looking for a 0, but unfortunately here it did not happen. So we have not made any progress. We are still staying in S1, okay, because 1 1 1 is coming continuously here, so we are still not making any progress, staying at S1. But the moment when we come here, we get a 0, 1 followed by a 0, that is an encouragement. We have proceeded in the right manner from 1 to 0. So that is the state S2, which denote the detection of the first 2 bits. Okay, first 2 bits. Okay, in our case it is 1 0. Then S3 is again denote the detection of the first 3 bits. Okay, now in Mealy machine, that's all what we require, because after detecting the 3 bits, if X now becomes say, so in this case, if I write down this the detected bits, so in bracket, so here I am detecting okay, 1, I am detecting 1, and here I am detecting 1 0, here I am detecting 1 0 1. So I have detected so far, and if the next bit is 0, my job is done. So if the next bit means the present input is going to become 0, I have already stored the data related with the past 3 bits in the flip-flops or in the storage element. So 1 0 1, I can combine it with the present input and generate the output to become 1. So I don't need a separate state to store the information of 1 0 1 0, because I can have a combinational circuit which take inputs from the external input as well as the state of the flip-flops. So state of the flip-flops will give me the detection of the first 3 bits, and then when the external input, current input is becoming 0, in this case 1 0 1 0 can be detected. So with the help of combining both the state outputs as well as the external input, I can detect the required sequence. So I only require 4 states in the design of Mealy FSM. So let me complete the step 1 by what is the step 1? Draw the state diagram. So I just designated the states, what is states mean, and then now I'm going to use those S0. So let me put in those states: S0, S1, then S2, S3. Okay, so these are the 4 states. Now I am going to draw the state diagram. Okay, so what is S0? No detection. So if when we are here, if 0 is coming, I am not making any progress. So I will denote it as like 0 is coming, and so this means x equal to 0. After, when we are here, if continually x equal to 0, then we will continue to remain here. That's what we are trying to say, and our output is going to be 0. But when I am here, if I'm fortunate, I can get a 1, x equal to 1, and then I made a progress to the next state, but still my output is 0. And when I am at this state, I can have 2 options. Either the next bit is 0. If the next bit is 0, that's good, because that is the second bit I was looking for. So x is equal to 0. I made one more step, progress, but y is still 0 because I have only detected the first 2 bits. But if when I am at at S1 state, if the next bit is 1, then what happens is that I have to continue to stay here, because when x is equal to 1, I have only detected the first bit, and since I am taking the overlapping, so I am going to stay at S1, but y is again going to be 0. Now when I am at S2, again I have 2 options. Either a 1 would come, 1 is what I was looking for. So if 1 comes, then x is equal to 1, y equal to 0. So I have detected basically 3 bits. So that's what I say. But when I am at S2, if instead of 1, if I am getting a 0, so that means 1, 0, 0. And 1, 0, 0 is such that this has broken the pattern. And where can I go back? I have to go back all over to S0, because it is as good as now detecting and not even a single bit. Okay, so if I get s is equal to 0, so that means 2 consecutive 0 comes, and that is nowhere part of my sequence, and therefore I need to start all over again, and y is equal to 0 definitely. Now when I am at S3, so I have detected basically 1, 0, 1, and if 0 comes, I have detected the sequence. So if 0 comes, I have detected the sequence, and since I am considering overlapped detection, where should I go? I can go back to the case where I have detected 2 bits. So if I get if I get a 0, I have detected, therefore y becomes 1, 1, 0, 1, 0. So when I am at S3, it is 1, 0, 1 is detected, and again x equal to the current input becomes 0, means I will combine the information in S3 with x, the current input x0, and make y equal to 1. So y is a function of not only S3 but also x equal to 0. And I go to S2. Why do I go to S2? Because I can consider the 1, 0 of the last 2 bit as part of the forthcoming sequence, first 2 bits. So that is why I am going into S2. Okay, so like one case in the example I have shown here. So after detecting this first sequence, okay, I go back as if now I need only to continue after the 2-bit sequence, because this 10, which is part of the last part of the second half of the first detected sequence, can be considered as becoming part of the first part of the next detection. So that is why I go back to S2. Okay, but in case if x is equal to 1, then what I am getting is like 1 0 1 0 1 1. Okay, so if I get 1 2 consecutive 1 means it's as good as like detecting only a single bit. So I need to go to S1. So let me just modify this drawing a little bit. I will draw this the other side. So if x is equal to 0, I make y equal to 1 and go to S2, and then if x is equal to 1, I have 2 consecutive 1, so that means I can only take the first bit or the last bit as part of the detection, and y is equal to 0. So you can see that from every state, wherever state I am, so the state means it's the state of the memory element, okay, storage element, and when I am at any state, I can have an input coming which is 0 or 1. So from any state there is 2 outgoing arrows, one for x equal to 0, one for x equal to 1. So here x equal to 1, x equal to 0. Here also x equal to 0, x equal to 1. x3 also x equal to 0, x equal to 1. So these are the options by which I can change the state. So now the next step is from the state diagram. Yes.
Can you explain it from S1?
S1. Okay, S1 means I have detected the first bit in the required sequence. What is my sequence? The sequence I want to detect is 1 0 1 0. So whenever I have detected the first bit, that is 1 in this case, I move to S1. If continuously 1 is coming, I have not made any progress from there. I only detected 1 bit. So that's why I am still here. But if I get 0, I detected the first 2 bit, I go to S2. Okay, so 1 0. And if 0 comes again, I will have to go back to S0 because it is like 1 0 0. And 1 0 0 means 2 consecutive 0 is never part of this sequence. Okay, we have not even begun the sequence, so we have to go to S0. But if I get a 1, I made progress. From 1 0 I have gone to detection of 1 0 1. Okay, this 3 bit is detected if I get x equal to 1. So now I am waiting for the last bit. The last bit has to be 0. So if 0 comes, I make y equal to 1, and after making y equal to 1, I will again look for a new sequence which starts with this 1 0. So I have detected this sequence, so made y equal to 1 here, and then I will consider the last 1 0 as the first 1 0 of the next sequence and see whether I can get another 1 0. Is that clear?
From S2 and S3, if x equal to 1, y 0, the second part, the x1, y0, means from S3 to S1.
This one or this one? S2 to S3. This is S2 to S3.
S3 to S1.
S3 to S1. This one, yeah. So this is when I have detected. I have already detected the first 3 bit 1 0 1. After that, I am getting another one. So it's like 1 0 1 I have already detected, but the next bit came as 1. Now this is not the sequence, so we failed detecting the sequence. Now where can we go? we can make use of this one. That's the maximum that we can take benefit from the whatever data that has come, right? If I take 1 that's not part of the sequence, so I cannot take more than that. So I will not go back to S0, I will go to S1, because I will make use of the last one as the beginning. I can have a 1 0 1 0 coming like this and detect the sequence, right? Clear?
Yes, sir.
Okay, so we have done the first step. We have drawn the state diagram for the Mealy machine. So if it is Mealy machine, this is how we draw the state diagram. And now let's go to the step number 2. And now what is step number 2? Is draw the state table. So same information in a tabular form we can put in. Whatever information is in the state diagram, we can put in the same information in the form of a table. So that's what is called state table. So whenever we draw the state table, we need to assign some bit values for S0, S1, S2, S3. So, and you can do it in any fashion, but the simplest way we can think about is that S0 means 0 0. There are 4 states, so 2 bit is enough to represent 4 different states of a flip-flop. And now I am giving I am assigning actual values for those flip-flop state output. S0 means the flip-flop is at 0 0. S1 means the flip-flop is at 0 1. S2 means it is at 1 0. S3 means it is 1 1. Okay, so I have assigned these, and once I assign it, I can draw the state table. So there are 2 bits for each state. Along with that, we have an external input, and depending upon the external input and the present state, the next state will change. Okay, so that's basically the idea. And therefore I will put X. Then I also need to name the flip-flop. So maybe I can call this as A and this as B. So QA is the state of flip-flop A, and QB is the state of flip-flop B. Okay, so I can have 8 different combinations: 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Okay, all right, so now we need to give the information concerning how the states change depending upon the present state and the input that is coming. The state is going to change, and so the new state I'm going to denote it as QA plus and QB plus. Okay, and I have an output also which depends upon the X and the previous state, and that I will call it as Y as before. Okay, so how does the state change? When I am at 0 0, that means S0. When I am at S0, so here I am at S0, here I am at S0, here I sorry. So here it is S0, then S1, S2, S3. Okay, so when I am at S0, if 0 is coming, what is happening? If 0 is coming, I stay at 0 0 only. I stay at 0 0 and output is going to be 0. When I am at 0 1, which is my S1, and 0 is coming, then what I do, I proceed to S3, which is 1 0, but still I have not detected the sequence. When I am at 1 0, so 1 0 means S2, if 0 is coming, that means 2 consecutive zeros, I go back to 0 0, output 0. When I am at S3, that means 1 0 1 we have detected, 1 0 1 we have detected, and then I am getting another 0, means my output will become 1. And where do I go? I go to 0 1. Okay, I go to S1. So that is this one. Okay, sorry, not that, this, sorry, I go to S2. Okay, so I have to do it carefully. So I am at S3. Okay, S3 is basically 1 1, and if I get 0, so this ticked one, y become 1, and I go to S2. S2 is 1 0. 1 0. Okay, so then next is I am at again 0 0, and if I get a 1, so now the input is 1 here. If I get a 1, I move to 0 1, output is 0. And if I am at 0 1, that is S1, I get a 1, I stay at 0 1. Okay, when I am, so that is this. Okay, I am at S1 and x equal to 1 came, I stay there itself. Okay, and then the next case is like 1 0, that means I am at S2 and I get a 1, so I move to S3, which is 1 1. So but here it is 0. Then I am at 1 1, and then I get x equal to 1, then I go back to S1, which is 0 1, output is 0. So this is my state table. Okay, the same information after assigning values for S0, S1 and S2 and S3, we write the same information in the form of a tabular column. Okay, so there is nothing new here. All that is shown in the diagram we have put into the state table. And step 3, so step 3 is the excitation table. Now excitation table is going to depend upon which flip-flop we are going to store that information. We can use T flip-flop, D flip-flop, JK flip-flop for A and B. Okay, storing the QA and QB, it could be the output of any of these flip-flop. So depending upon that, the step 3 will differ. So I will use D flip-flop, so that's the simplest. So D flip-flop has DA input and DB input. So we need to find out what should be the input that we need to give so that we will get the state QA changing to QA plus, and QB, that is a previous state, goes to the next state QB plus. Okay, so we are now looking at basically QA going to QA plus and QB going to QB plus. So in order to achieve this change, it's very easy to write in the case of a D flip-flop. If it is JK flip-flop, you need to keep in mind what is the required two inputs, J and K value, for making this change. If QA is the output of a JK flip-flop, then for QA, which is right now at 0, to change it to 0, what should be my options at the input for J and K? You need to put in here. So there should be a column for JA and KA, and similarly JB and KB. So there will be two additional columns, and you need to know what should be the input. But if it is a D flip-flop, you know that what you give at the input, you will get at the output. So if you want this output to be like this, you give the same thing. So it will be just same as the QA plus 0 1 0 1, then 0 0 1 0, and dB will be 0 0 0 0, and then 1 1 1 1. Okay, so okay, so this is the input that we should give to the D flip-flop in order to get the required change of state. Okay, so first we draw the state in a state diagram, and then put in those same information of the change of state in a state table, and then now we are writing the excitation table. Okay, so the final step is basically to come up with a circuit which will basically implement these DA and DB and also Y. Okay, so Y is also involves a circuit. So there is a combinational circuit part. So far we only talked about the sequential part, which involves two flip-flops A and B, and we said that they are going to be D flip-flops. So they are QA and QB are the output of D flip-flop, and then the output of the D flip-flops we need to connect to some combinational circuit to generate the required DA and DB inputs, as well as the external output Y. Okay, so to generate that, so we used the Map simplification. For example, if Y, so this is our independent variable, and these are our dependent variable. Okay, so these are treated as the independent variable. So we are talking about a function. So these are the function output, and these are the function inputs. Okay, so for the combinational part. Okay, dependent variable. But what I mean by independent variable is that for the combinational circuit, it will take some inputs. So that inputs will be external input and the state of the flip-flop. Okay, so I should make it maybe clear, saying that input to the combinational circuit, and here it is output of the combinational circuit, output of the combinational circuit. Okay, so now let me okay, so let me design now. So what is my Y? So Y depends, Y is a function of X, QA, QB. So what is that? I need to find that out. And then what is a function of DA? It's a function of QA, QB. So these three functions, Boolean functions, this is just like any combinational circuit design. I can use a multiplexer also to design this. Okay, so this is also depending upon X, QA, QB. I have the truth table here. So if I want to design using multiplexer, that may be a convenient way. So let me just continue here. Okay, so the design of Y. So let me take the design of Y. So maybe you can write it as a new step. Okay, so let me just write it as a new step, step 4. Design of the combinational circuit part. The sequential part is already fixed to be 2 D flip-flops. So now we need to design the combinational circuit part, which will generate the output as well as generate the input for the the storage element. Okay. So first of all, so I'm going to use multiplexer, so that's very convenient. So I can use say 4x1 multiplexer. So I will use a 4x1 multiplexer, and to this multiplexer I will give my QA and QB, the state of the flip-flops as the select inputs. So I have 1, 2, 3, 4, this, and my output is going to be Y. Okay, so this is my Y output. Now look at Y here. Okay, so here since I have given QA and QB as input, it's slightly inconvenient. If I had given X and QA, that would have been better, but okay, so we will manage it. So what we need to do is basically look for 0 0 case. So this is 0 0 and this is another 0 0. So when QA QB is 0, what is my X and Y relationship? Y is equal to 0 when X equal to 0, and Y equal to 0 when X equal to 1. So that means it doesn't depend upon X, it is always 0 when QA QB equal to 0. So I can give a I can give a 0 at the input. Next case is QA QB is equal to 0 1. So that is this case and this case. And look at Y. Y is 0 there, and Y is 0 here also. Again, it doesn't depend upon X value. So I give 0. I give 0. The third case, as you can see that Y doesn't depend. In this case also, I will have 0. The last case 1 1. If you look at when QA and QB is 1 1, my X when it equal to 0, I get Y equal to 1, and when X equal to 1, I get Y equal to 0. So it means X bar or so basically I need a complement operation of X. So that will be the input. So we got our design of Y, combinational circuit for designing Y. So I am implementing the combinational circuit using a 4x1 mux. That's very convenient. Okay, so similarly I can design the input for the D flip-flops. So DA and DB, same procedure we follow. So DA, if you look at first of all, it is going to be 0. so this is going to be DA, and I use a 4x1 multiplexer. Again I give the same input for this also. And as you can see from the state diagram or state table, my DA is 0. My DA is 0 here as well as here, so that means it doesn't depend upon X, and therefore I'll also give 0 here. Then when it is QA QB is 0 1, so that is these cases. So when X equal to 0 it is 1, when X equal to 1 it is 0, so it's going to be the complement. Okay, so this is going to be X bar again. The next one is 0 1. So 0 1 means it's X, so it's going to be X. And the last one, if you look at, it's going to be 1 0. Okay, 1 here, 1 here, and 0 here. So when X equal to 0 it is 1, and X equal to 1 it is 0. So this is like the second case. I will have X bar here. Okay, so you only need one NOT gate to generate all the X bar. So let me generate it. So this is my X bar. I can give to all places where X bar is required. Okay, so I only need a one NOT gate to do that. Next. Okay, so now the last one remaining is my design of last 4x1 max. So now the output is going to be DB. Again it has 4 inputs. So you have to look at the state table and the excitation table together to see that, and you can see that when X equal to 0, how is it, when it is at 0 0, 0 0, it's going to be 0 1, 0 1, it is going to be 0 1. So everything is like X. Okay, for all the states it's X, you can see that. So if you look at this and this, when X equal to 0 it is 0, when X equal to 1 it is 1. Similarly for 0 1 also, X equal to 0 it is 0, when X equal to 1 it is 1. So you just need to give X everywhere. So okay, X is given everywhere. So this is my combinational circuit. So I have done my combinational circuit. So earlier I have, when I drawn it as the combinational circuit as a block diagram. So I can put all of this in a block diagram. So this is my combinational circuit. So I have some combinational circuit part in this sequential circuit, and then I have other things. What is the other thing? I have basically the storage element. The storage element. So the storage element is basically two flip-flops. So this is my DA, and I will have QA, and there will be a clock here. So then DB, QB. Okay, so that's the combinational part. So here we keep the clock, and then the remaining connection is that I have this select input, which is basically taken from the output of the flip-flops. So this is my QA, and QA should be connected to this point, and this is my QB, which should be connected here. Okay, so these are input. These are inputs to the combinational circuit, and this is the output of the combinational circuit. So now I can represent the storage element also in a block. Dotted lines. So this is my storage element. So this is my melee machine. Okay, just if you look at there's two parts. One is the storage element part, the other is the combinational circuit part. Okay, and the output we are obtaining from the combinational circuit. Okay, so this is the output, and the input, external input, is given to the combinational circuit, and to the combinational circuit I have also the inputs from the state. Okay, so this is earlier I have shown it this side, but maybe it may be better to show that way, but just the way of drawing. But essentially it means the combinational circuit takes input from external inputs and also from the state of the flip-flops. So let me just write, this is the storage elements. Okay, the storage elements take a input from the combinational circuit, and its output is given to the input of the combinational circuit. So these are the inputs. These are the inputs. Maybe I will make it better drawing, right? It looks better if I Okay, so outer one is A and it is connected here. This is B, it is connected here. Okay, so that way you can see that these are state inputs. State inputs. These are external inputs, and then this is the input to the storage element. Okay, so and this is the clock input. Okay, so you can see now, I think it's clear now. So you can compare this with our initial diagram which we have drawn for the melee machine, which is this. Okay, so external input is coming to the combinational circuit and it gives you external output. In our case it is Y, only one external input X, and then the storage element output. I have not completed this. The storage element output goes here. Okay. So that those are feedback. Okay, so same structure you can see here. This block is basically the combinational circuit. Okay, so in a similar way we can go ahead and design our Moore machine also. So let me just draw a line. We have nearly half an hour, so we can continue. I should have done all this before. But bear with me. Okay. So now we are going to look at how we can do with the same design in as a Moore machine, Moore finite state machine. Again, it is going to be finite states. So let's take the same sequence. And first of all, the step number 1 is to draw the state diagram. But here for Murray machine we will have a slightly different state diagram. So we will start with S0, and since the output entirely depend upon now the state, I will also assign what is the state output, because it solely depend upon the state in which the machine is going to be. So if it is at S0, output is 0. So S0 means no detection like before, and then I will go to S2 when S1. There also y is equal to 0. And when do I go? As long as I am getting only 0, I have not made any progress yet to detect the first bit. So I will just write x equal to 0. I will not say y, because y is tied up with the state. And if x become 1, then I get a single bit detection. I move to S1, and then if I am at S1 and then I get 1 again, that is like no progress. I remain at S1, but if I get 0, I get 2-bit detection, S2, but still my y is 0. So if x is equal to 0, I have detected 1 0. Now when I am at this state, if one more 0 comes, I lose all the progress that I have achieved. I need to go back and wait for the first bit detection. Okay, I have detected nothing if again x equal to 0. But when I am at S2, if next bit happens to be 1, I detect 3 bit, but still my y is 0. Okay, if x equal to 1. Okay, so S2 means it's 1 0 is detected, and after that one more 1 came. I went to S3, but still I have not detected the sequence. I have only detected 3 bits. So to detect the sequence, I need one more state where y becomes 1, and that happens if a 0 follows. Okay, so you can see that the sequence is clearly here. First bit 1 0, second bit, third bit, fourth bit. So 1 0 1 0 is our sequence, and we reached S4. And when I am at S3, after detecting 1 0 1, if I get one more 1, then I should I should go back to this state. 2 successive ones makes me to land up in S1. And now I am at S4, that is 1 0 1 0, and then if I get next bit as 1, so that's like getting 2 successive ones. I have already detected 1 0 1 0, but now the next bit, if it happens to be if it happens to be 0 1 0 0 0, so 0 0 means I have to go back to the beginning. So this is for x equal to 0. But instead of that, if I get another 1, 1 0 1 0, and then I get 1 0. So let me just write it here. I have 1 0 1 0. I have detected. The next bit is 0, means I have lost all progress back to square 1. But if it is 1, then I can consider this 3 bits as my next states. So that means 1 0 1. So I can go back here. So I can come back here if x equal to 1. So this is my state diagram. So if I am at S4, that means I have already detected the sequence one time. If the next bit is 1, then I can make use of these 3 bits as starting of a new sequence. Okay, so that's why I am going to S3, because S3 corresponds to detection of 3 bits. But instead of that, if it is a 0, then 2 successive 0 is not part of the sequence. I need to go back to the beginning. Okay, so I have the state diagram. It is slightly different for Moore FSM, finite state machine. Now the rest of the procedure is going to be exactly similar. You can decide the flip-flops you want, but before that, here you will notice that we have 5 states, and for 5 states we require, so this is a knot, we require at least 3 flip-flops. So let's call it as A, B and C. Okay. So first of all, S0. I'll call it as S000, S1, 0 0 1. I can choose whatever way I want. Then S2, if I want, I can choose 0 1 0. That is also possible. Or S3, I can put 1 1 also, 1 0 0 also. Any of the distinct 3-bit combination I can use, but let us put 0 1 1 and S4 1 0 0. So you see that Moore machine require more flip-flops because it require more states, and so design becomes slightly more complicated because of that. But the procedure is exactly the same. So next thing we need to do is basically to write the state diagram. So right now, when we write the state diagram, let us put A, B. So these are the outputs of the flip-flops, the present state of the flip-flops, which depends upon the past inputs, and then X value. Now the advantage here is that for Moore machine, X is not an input variable. Okay, for deciding the output function, but it is an input variable to the combinational circuit. Okay, but combinational circuit is only need to be designed for the next state. So I will just directly write dA, dB and dC, because I know that QA plus is basically same as dA, so that's why I am doing like this. Since there are 4 input variables here, which will decide my DA, DB, DC, I have a lot more of combinations. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and then 1, 0, 0, 0, 1, 0, 0, 1. All the 8 combination I have to. Okay, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Alright, so I listed all the inputs, and now I need to list the next state, which is same as the input to the D flip-flop. Okay, ideally I should write so I'm just combining the state table and the so this is step number 2, where I've combined state table plus excitation table. So you need to decide the flip-flop. If you make a D as the flip-flop, excitation table writing is very easy. It is same as the next state. Okay, so and what is the output? Output is basically S4. Whenever it is S4, S4 is what? S4 is 100. So Y is basically A, B bar, C bar. Okay, so it just depends upon the current state of the flip-flops or the storage elements. It doesn't depend on the input. Okay. Whereas DA, DB, DC, input to these flip-flops, we need to find out. Okay, so suppose AB. So AB equal to 0, 0 means AB. So 0, 0, 0 is what I call as S0. So let me just write the states here sidewise. So this is basically S0, and this is S0, and the next one is S1, and the very next one is S2, S3, and then S4. Okay, so these are the 5 states, and for all the other states I don't care, because my flip-flop, I don't want it to go into those states, so it doesn't depend upon this. So it will not go into those states. So I can put X here. I only require 5 states. Okay, so I don't want all the other remaining 3 states. I don't use it. That is 1 0 1 1 1 0 1 1 1 0 and 1 1 1. Those states I'm not going to use, so I will put don't care cases. Okay, so we have chosen 5 of the 8 states, and then now I need to see how the changes happens depending upon x. If x equal to 0 when I am at S0, it will remain there. If x equal to 1, I go to the next state, which is S1. The corresponding thing is 0 0 1. Okay, so that is now when x equal to 0, I go to S2. S2 is basically 0 1 0 0 1 0, and if it 1 comes, I should remain there. So that means 0 0 1. I should remain there. Okay, when I am at S1, if x equal to 0, I should remain at S1, otherwise I should go to S2. Now when I am at S2, if 0 comes, I should go to 0 0 0. I should go to S0. If 1 comes, I move to S3, which is 0 1 1. Okay, so next is when I am at S3, if I get 0, I make progress and I go to 1, so I go to 1 0 0, which is S4. But if I am getting x equal to 1, then I go to S1. And what is S1? 0 0 1. 0 0 1. Okay, finally, if I am at S4 and I can get a 0 or a 1. If I get 0, I go to S0. If I get 1, I go to S3. If I get 0, I go to S0. Otherwise, I go to S3, which is 0 1 1. Okay, so that's the same information. I am putting it in a tabular form, and I am writing straight away the excitation table without writing A plus, B plus and C plus, which are the next state of the flip-flop, because excitation table of D flip-flop says that only I will get what I give. Okay, the next state is what my current input is going to become the next state. So I'm directly writing the excitation table to make it fast. Okay, so now again we need to design this DA, DB, DC. So what should be my design? I can use multiplexers, but now I should use at least 8x1 multiplexer to do it, or let us just use K-map and solve it, okay, and implement it with gates also. So that is another way. So the way you implement the combinational circuit, it is up to you. I have shown various methods. So we will basically get dA, which is a function of A, B, C and X. It's a 4 variable function. dB, again A, B, C and X, and DC also a function of the 4 variable. Okay, so the next state, how does it depend upon the present state of the flip-flop and the input, current input, whereas the y is only a function of ABC. So that's the difference. Y is only depending upon C. It doesn't depend upon X at all. Okay, so that's more a machine. So to complete it, you need to find DA, DB, DC. So it's going to be, so let me just compress it into it. Okay, so let me do it with a K-map this time. Or let's do it the other way itself. That's more better. So I need an 8x1 matrix. I'll have input DA. I have 8 inputs, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what should be my inputs? So if you look at, so this is 0. This is the advantage of the multiplexer method. I just need to look at the DA column, and the first two, if it is 0, it is 0, again it is 0, again it is 0, again it is now it is 1 0, so that means X bar, and then again 0. After that everything is X. So done. If you use K-map, then you need to minimize it and find all the POS, essential terms. So this is faster. So next one for DB, again I have 8 input, 1, 2, 3, 4, 5, 6, 7, 8. So now I look at the DB column. 0 0 means 0, then 1 0 means X bar, next is 0 1 means X, next is 0 0 means 0, then 0 1 means X. Okay, and the last three, X is looking just the same as don't care condition. Okay, so let us do something. Let's just leave that. Okay, so we will just leave that because we don't care, so we will just leave that, because we are not going to give that combination of select input. This is going to be ABC. Okay, so this is going to be ABC, and we will not give ABC as corresponding to the last three inputs. So there's no, it doesn't matter what is going to be the input there, but in order to get the function we need to give all the first 5. Okay, so there is one more. So that is DC. So let's do that also. So DC, again there is 8, 1, 2, 3, 4, 5, and then the other one are there, but we don't use them. Okay, so now we look at the DC column here. So 0 1 means X, next is again 0 1 X, then again 0 1 X, 0 1 0 1 X, X, that's it. So the other ones we don't care. If you give 0 or 1 or X, it doesn't matter because it's not going to depend upon it. We are not using those states. Okay, so that's all my combinational part, and now comes the sequential part, or the storage element. So let me put it here. 3 flip-flops. So 3D flip-flop we are using. So it has DA, DB, DC. So this is my A out, B out, C out. So DA will give, DB will give, DC I will give. So that is my storage element. So like before, I would like to draw blocks to show, and finally there is one more thing. I have an AND gate with B bar and C bar and then A. So this is gone into an AND gate. That is my Y. Okay, so now let me just draw blocks. This is my combinational circuit. Oh, it's combinational circuit part, and then this is my storage element, and finally I have one more block, which is another combinational circuit, which only depends upon my combinational circuit. So here I will have additional inputs from the output of the flip-flops, so I should show that also. Okay, so let me show that. Okay, so these three I will have to give as input. And then the drawing may be looking very bad, but okay, so the outer one is connected to A, B. Okay, so this is basically the complete circuit. I have only one external input, which is X. Okay, so that I can show here. Maybe I will make this like I need to use one more NOT gate. And then X here and X here. Okay, so Okay, so this is my external input, and these are my state input. Okay, that will generate my the storage element input. So these are my storage element input, 3 input, DA, DB, DC, and then the output only depends upon the state output. Okay, output from the state controls my final external output. Okay, so that's it. So this is the block diagram I started with today when I said about the Murray machine block diagram. So you can see that there is a combinational circuit which take external input as well as the state input, and then it goes okay, the DA, DB, etc. It is obtained from the combinational circuit, which generates functions which depends upon X as well as QA, QB, QC, and then the final output, external output, depends only on the state output. So that's basically the Murray machine.